Let's talk about how we process information in scientific computing, or specifically, how we go from our hypothesis about something through the process of making information or deriving conclusions. So first of all, of course, you need to have a hypothesis. We will not dwell in detail on a hypothesis and how we formulate them in this course. For this time, we assume that you have some idea that you want to test. For example, that some model of traffic on streets in the city will be able to predict traffic jams on the roads in case of some change in the road grid structure. That is, of course, under the assumption that the model is first tuned in accordance with input data. The data might include the tracking of movements of individual cars and traffic flow rates from actual streets. And you will have geographical information and information about lanes. And to test that, you need first to build a model of the system, formulate it in mathematical terms, and then parameterize it. And finally, you need to conduct a critical experiment with your model. For example, you predict that if the city closes down one of the streets, the traffic will change in this way or in that way. Of course, conducting experiments designed on purpose might not be realistic. Then you can try to predict the impact on traffic flow during the construction phase of some buildings, when part of the street will be closed and the closure will reduce the flow. Then you can record what your model predicted for this scenario, and after a while you can get actual measurements after the closure and see if your model managed to predict them successfully. You can conduct these kinds of experiments multiple times for different points based on the schedule of renovation works. As a result, you will either see that your model is correct and that it predicts everything fine, or you might find out that it fails to make an accurate prediction and that you need to either revise the whole model or parameterize it better using the newly acquired data. Eventually, although it might take a lot of time, you will end up with a model that works. Then you proceed to the following steps, like trying to figure out the limitation of the model and trying to make actual good predictions about the planned road closures and use that model in the planning of development of the road structure. But how do we go through this middle part, or collect data? How do we run the whole computational science part of things? How do we go from input data to the results of our analysis? The typical information processing workflow looks as follows. We'll start with data input. In our case, a data input would be, for example, the questionnaire in which people living in different areas of the city will respond which city areas they visit and how often. Then we will also have data about car flow, and that will be our primary quantitative data because questionnaires are not 100% reliable, but things you have measured on the streets are. Then you take this whole data set and you need to do something with that. Generally, the data will already be available in some digital format stored in some organization's database. Still, to process it, you have to move it first to your location. So you need to organize the storage of your data as well. And this is typically done with so-called databases. These are specialized software systems that are designed specifically to store data. And they don't do much else. They only allow you to write data into them and read data from them. As an additional feature, some of them provide some minor data manipulations like aggregations and filtering. For example, you can count how many data points you have, or you can do some simple numerical transformations. Like you can sum up some parameters, or you can compute the average of some parameters, but this is a secondary function. The primary function of a database is the storage of information. Once you have this data stored reliably, you can access it and take it multiple times and don't be afraid that you will lose something in the process. You can then start preprocessing data. We need to have this step because the data that comes is usually not 100% reliable. So, for example, if you have a dataset from some traffic monitoring sensors, there is a chance that at some point one of the sensors will be broken or not going to get access to internet. In such cases, the data might be missing or corrupted. Hence, you need to figure out what to do with these missing or corrupted data points. Once you have this data preprocessed and you, as a designer of the system, consider it ready to be used in your scientific application, you need to store it back into the database. The preprocessed data needs to be in the database as well, because you need to distribute this data and some pieces might require distributing some parts of it multiple times. It also depends on what kind of system you have. Suppose you have simple parallel software where everything happens on the same computer, or at least in the same physical location. In that case, you might get away with some local storage of preprocessed data on shared media like a hard drive. On the other hand, if it is a distributed system or a cloud computing solution, then this part might get very complicated, especially when computing nodes or cores do not have direct connections to each other or the database. For example, you will not be able to just read data from the database directly in more sophisticated clusters. Instead, you will need to have data passed around the system with some local network that connects, for example, only nearby nodes of that cluster. After the distribution phase is done, after every node has received its task, you need to perform calculations on those nodes. For that purpose, you would need to provide every node with the executable code in addition to the data. For example, in our case, you might want to apply the model's input parameters to the equation and implement what is called time-domain numerical simulation of your model over some time. So you will provide the core code that will take one set of input parameters and initial state, run the simulation, and return the outcome you are interested in. For example, you can model individual cars and their routes, speeds, locations, and so on. And after you do that for multiple iterations, you will get some results. For example, you will get the number of cars that traveled through a given street for every 20-minute long modeling interval. Once you have the results calculated, you need to write them back into the database. It is a stage of accumulation of results, and you need to extract data from the node somehow into the database. Depending on your problem and the amount of data you receive from individual computations, it might also be tricky. It might be especially challenging from the aspect that you might have limitations on the write capacity of your database. So it would be best if you thought carefully about storage architecture, as some options will provide you with more distributed options than the others. Now, once you have collected the processed data into the database, you end up with the last task to post-process and analyze data. It might also be a small scientific computational problem, similar to what you have done just in previous stages, but at a smaller scale. You also might change the properties of your post-processing to represent the outcomes better. In general, post-processing includes operations like aggregation of data points, computation of statistics about predicted parameters, or comparing computed statistics to measured data. It usually is much less computation intensive, but it still can be distributed because, well, once you have a distributed system at your disposal and the setup, why not use it for more than just setting up main calculation? You can do a lot of post-processing and pre-processing actually as well with a distributed or parallel system. And the final step is once you have that post-processed data, once you have some output in the form of tables and plots, you need to interpret them. And this is the part that cannot be solved by computer. You have to do that part yourselves as engineers, scientists, or analysts. It is for you to interpret what's written there. You and only you know, for example, what kind of assumptions you made when you made the models, what kind of assumptions you made about the data. Hence, only you can say what the plots really mean.